Welcome to Management 670 Business Analytics, and today we'll be talking about measures of variability, how data is different from one another. So let's get started. Variation, also known as dispersion, is a way to describe how the data is laid out through a frequency channel. It's different than the central tendency, which is about finding the middle or one exact point that will describe the center, and it doesn't have any mention towards the shape of what a data set looks like. Variation is about how spread out the frequencies are for these values. First up, we could talk about the range. It's a measure of dispersion, which is not as common as variance and standard deviation that we'll get to. But it does provide some benefit because it tells you how long of a range, how long of a distribution we are talking about for these values. You take the largest value, doesn't have to be the first one or the last one, just the largest value in a series of numbers, and subtract the smallest value. That's your range. It does ignore how the distribution is actually shown though. So my description right here at the bottom, they have the exact same range. The maximum value for both of these sets of data is 10, the smallest is 7, so the range for both is 3. But you could tell that the distributions themselves are fundamentally different, so range is only so applicable. The interquartile range is like the range, but instead of finding the largest value and the smallest value, this looks at just the middle 50% of the values in a data set. It takes the third quartile, subtracts the first quartile, and therefore, by definition, you have the middle 50% of the data there. It's not affected by extreme values, either large ones or small ones, so outliers don't really influence the interquartile range. Let's demonstrate this in a problem. Thinking challenge problem 1. Again, we're an analyst for Craner Securities, and we have the same data as before for the stock prices. What's the interquartile range of these stocks? Well, in order to calculate that, we have to take the numbers themselves, the prices that are listed. We have to order them ascendingly from smallest to largest, and then we calculate Q1 and Q3. So the first quartile is 2.25, so it's closer to the second observation than the third, but in the end we can calculate that to be 12.25. And then quartile 3 is closer to 7 than 6, so it's 6.75. With the formula used to calculate what the quartiles are, we can find out that that is 17.75. So just the difference between those two is 5.5. In 5.5 range, 50% of our values pop in there. Here's a box plot of the prices themselves. I've added the Q3 and the Q1 values. This large blue box right there for the box plot is our 50%. All the numbers are listed, ordered from 11 all the way up to 21. Our range, therefore, would be 21 minus 11, or 10. But there's 50% of our values will fall in that 5.5 range between 12.25 and 17.75. Finally, the most common measure of dispersion, probably the one that you think of, is variance and standard deviation. It considers how the data is distributed by using all of the observations in the data. So therefore, it is very much influenced by large or very small outcomes, those outliers. Variance and standard deviation describe how the data varies from the mean itself, whether that's the population mean, represented by the Greek letter mu, or the sample mean, which is x with a bar over it. Picture right here, that balance point with the green triangle is the central tendency for it. So we need that mean. How do those yellow balls, how far away are they from the actual mean? We have two cases. Population is defined when we have all of the members of a specific group. It's the entire group, as opposed to a sample where we're taking just a few, some subset of the overall group, but then making inferences about the overall population. In most business cases and most applicable or stats situations, we're dealing with the data set that should be considered the sample, but occasionally we will have population data. When you have population data, you use Greek letters. So when it was population mean was mu, standard deviation for a population is the Greek lowercase letter sigma, and variance is just sigma squared. We differentiate between population and sample size by a capital N for population and a lowercase n for sample. The calculation for the population variance is sigma squared and then the sum of all of the differences between the observed value and the sample mean, or the population mean. And you square that. You square that because it gets rid of the negative distances. We don't care about those. We just want to know how far away each observation is from the overall mean. And then you just divide by the total sample size, large N. That's different than what the sample size is. Notice that it's the same kind of setup. You have all the observations. You subtract the sample mean, in this case, x bar. Square that. Again, you want to have positive distances. Then you divide by n minus 1. When dealing with the sample, we're using x bar for the sample mean, s, just lowercase s in the English language as standard deviation, and s squared as the sample variance. Again, the sample size is lowercase n. Let's look at an example. I have 6 values here, and I want to know the variance. How is this data dispersed around x bar? Well, we can just take the regular average, and that would be 8.3 in this case. And I can use the formula from the previous slide and make a very large calculation for S2. I start with that first observed data point, 10.3. I subtract the sample mean, 8.3. I square that difference. I do the same thing for 4.9, subtract the sample mean, square that, and do that for all the observations, 8.9, 11.7, 6.3, and 7.7. Then I divide by 5. That's n, the sample size of 6 minus 1. And now I come to my sample variance, which is 6.368. Challenge problem number 2. Same situation. We're an analyst, and we have these stock values. What's the volatility of these stock prices? There are my prices right there. There's no need to order. I can find the average to be 15.5. That's my sample mean. Subtract the sample mean from each one of the observations, square, sum all those up, and divide by 7. This gets me to a variance of 11.14 and a sample standard deviation of 3.34. If we load these values, these 8 values into Minitab, run display descriptive stats with the following options. We want to include the mean, of course, but want to have the standard deviation, the variance, and let's go ahead and click on the interquartile range. I'll add that as well. And just to see what this distribution looks like, we can choose a graphing option. We'll do the histogram of data. There's my summary stats right there. There's my mean of 15.5. I have my standard deviation of 3.34, along with the correct variance of 11.14. Lowest value, the minimum, I got Q1. There's the median. I also have Q3. And off to the right, here's a histogram with only 3 bins, so only 3 little areas, and the frequencies for each one. They're centrally located, really close to our 15.5. We have more, in this case 4, different values that are closer to our actual mean of 15.5. This looks fairly symmetric. So in conclusion, variability measures how far apart the different observed data points are from the overall mean. Thank you.